Hello, everybody. Welcome back to Learning as a Hobby. Today, in this video, I'm going to finish up the exercises for Chapter 3 in Spivak. So this will be part 2 of the video. I already posted part 1 last time, so you can check that out on the channel if you want to. I'm going to finish up the last 4 exercises that I chose to go over in Chapter 3 for Spivak in this video. So let's just jump right into it. All right, starting with question 315. So part A says, show that for any function f, that's equal to max f comma 0 plus min f comma 0. We defined what this means, what these functions mean in the last video, if you recall. Okay, this particular way of writing f is fairly useful. The functions max f comma 0, min f comma 0 are called the positive and negative parts of f. All right, so just going through the proof here, it's by cases. So if x is in the domain of f, then 3 cases here. Case 1, f of x, if f of x is positive, meaning that it's greater than 0, then if you look at max f comma 0 of x plus min f comma 0 of x, the max is equal to f of x because it's positive, and the min is equal to 0, so you get f of x plus 0, which is f of x. Okay, case 2, if f of x is negative, then max f comma 0 of x plus min f comma 0 of x is equal to, so the max would be 0 in this case because f of x is negative, plus f of x, and 0 plus f of x is, of course, f of x. All right, and then the last case, if f of x is equal to 0, then max f comma 0 of x and min f comma 0 of x, they're both 0, so you get 0 plus 0, which is 0, which is the value of f of x. And that exhausts all the cases. So that proves that that way of writing f works. All right, part B, a function f is called non-negative if f of x is greater than or equal to 0 for all x. Prove that any function f can be written f equals g minus h, where g and h are non-negative in infinitely many ways. And he gives a hint here for this. He says any number can certainly be written as the difference of 2 non-negative numbers in infinitely many ways. And so you just use that hint. So for each x in the domain of f, choose 2 non-negative constant functions, h of x and g of x, such that f of x is equal to hx of x minus gx of x. So in other words, you define f in this piecewise way, where all of the functions that you're taking the difference of are constant and non-negative. So you're just using that fact about numbers that you can do that. And since there's an infinite number of ways to do that with numbers, that means that there's an infinite number of ways to do this for any function f. All right, so that's part B. Okay, 316. Suppose f satisfies f of this functional equation, f of x plus y equals f of x plus f of y for all x and y. Let me just move this out of the way. Okay, part A, prove that f of x1 plus dot 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 plus xn is equal to f of x1 plus dot 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 plus f of xn. Right, and we'll do this by induction. So obviously f of x1 is equal to f of x1, so the base step is satisfied. The inductive step always starts with the inductive hypothesis. So assume that f of x1 plus dot 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 plus xn is equal to f of x1 plus dot 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 plus fxn for some natural number n, and consider f of x1 plus all the way up to xn plus 1. Right, so we can reassociate inside of the domain here. So that's the same thing as f of, in parentheses, x1 plus xn, all the way up to xn, close parentheses, plus xn plus 1, and then we can use the property that they gave us up here to break that up into this plus that. Okay, and by the inductive hypothesis, this part here can be written like that, and that shows that the theorem holds. Okay, so that's the inductive step. Part B says, prove that there is some number c such that f of x equals cx for all rational numbers x. And he gives a nice hint here for this because it's kind of complicated. The hint says first figure out what c must be. Now prove that f of x equals cx when x is a natural number, then when x is an integer, then when x is the reciprocal of an integer, and then finally for all rational x. So that's what I did. And I did it in that order. So let's take a look at that. So here's the proof. So starting with a natural number n, let n be a natural number, then f of n you can write as f of the sum from 1 to n of 1, and using the property that we proved in part A, I think it was, right? Yeah, part A. That's equal to the sum from 1 to n of f of 1, which is the same thing as n times f of 1. Right? Because when you sum a number with itself n times, you get n times that number. And this part here, you'll see ends up being the value of c. Okay. All right, so step 2, let n be an integer now. And then also we need this extra fact here. F of 0 is equal to f of 0 plus 0, which is f of 0 plus f of 0. And if you subtract f of 0 from both sides, that shows that f of 0 is 0. Okay, and 0 is equal to f of 0, which is the same thing as f of minus 1 plus 1. And then again, using that functional relation that they gave us in the instructions, that means that that's equal to f of negative 1 plus f of 1. And you can subtract f of 1 from both sides, which gives you f of negative 1 equals negative f of 1. Also, if n is negative, then f of n is equal to f of negative absolute value of n. And that's the same thing as n, the absolute value of n times f of negative 1, which is the same thing as negative absolute value of n times f of 1, which is n times f of 1. So that proves it for all integers n. Okay. All right. Part 3, here we let n be any integer minus 0, because now we're going to prove it for the reciprocal of integers, which is the third thing he told us to do. So then we use this fact. F of 1 is the same thing as f of n times 1 over n, which is the same thing as f of 1 over n added to itself n times. And again, using that functional relation, that's the same thing as f of 1 over n plus dot 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 plus f of 1 over n. And that's the value of f of 1 over n added to itself n times. Okay, and then so you divide both sides of this equation by n, and that gives you what you want. So f of 1 over n is the same thing as 1 over n times f of 1. Right, last part. Okay, so let p over q be rational. Then f of p over q is the same thing as f of p times 1 over q, which is the same thing as the sum of 1 over q, where the sum goes from 1 to p. That gives you p times f of 1 over q. And f of 1 over q is the same thing as, this should be a p here. This part is a p. That's the same thing as p times 1 over q times f of 1, which is the same thing as p over q times f of 1. Okay, and that proves the theorem. So there's a value of c for which that function is f of c times x, which is what let me just go back. That's what they wanted us to show over here. Right. So you just do it for each of those cases and you end up with what you want. 317 says assume f of x is not always 0, and that again they give us two functional equations now that the function has to satisfy. So we have the same condition as in 316, and we have this new condition as well. F of x times y is f of x times f of y for all x, y in R, and they want us to prove that f of x is equal to x for all x as follows. Right, so he leads us through the proof step by step. So first thing we need to prove is that f of 1 is equal to 1. Excuse me. And again, I can use this fact here. F of 1 is f of 1 times 1. And by the second functional equation that they gave us, that's the same thing as f of 1 times f of 1. Or in other words, that's the same thing as f of 1 squared. right? That implies that f of 1 is 0 or f of 1 is 1. However, if f of 1 is 0, then that implies that f of x is f times 1 times f of 1 times x, which is the same thing as f of 1 times f of x equal, and that since f of 1 is 0, that would mean that the function is 0 for all x, but that's a contradiction. Therefore, f of 1 is 1, because the assumption was that f of x is not always 0, right? So that means that f of 1 has to be 1, because that's the only other option. Okay, part B, prove that f of x equals x if x is rational. So by the 316, the one that we proved a minute ago, f of x is equal to f of 1 times x, but f of 1 we just showed was equal to 1, so that's the same thing as x, as long as x is rational, because we proved that for rational expressions in question 316. Right, part C, prove that f of x is greater than 0 if x is greater than 0. All right, so here's the proof. Let x be greater than 0. Then f of x you can write as f of square root x times square root of x. We can do that because x is positive, so it has a square root, right? And again, using that second functional equation, that's the same thing as f of square root of x squared. That has to be greater than or equal to 0 because it's a real number that you're squaring, right? And squares of real numbers are non-negative. If f of square root of x is 0, then f of x is 0 for all positive x. In particular, f of 1 of 0, but that contradicts part A. So that means that f of x is positive whenever x is positive. All right, part D, prove that f of x is greater than f of y if x is greater than y. All right, here I needed to have this little lemma here first. So f of negative y equals negative f of y, and I'm proving that down here. So 0 is f of 0, which is the same thing as f of y minus y, which is the same thing as f of y plus f of minus y. And then if you subtract f of y from both sides, so from here and here, you see that f of negative y is negative f of y. Right, so using that lemma then for the proof of what they want us to show, assume that x is greater than y, then x minus y is positive, which means that f of x minus y is positive. And that implies that f of x plus f of negative y is positive. And by the lemma, that's the same thing as excuse me, f of x minus f of y being positive. And if you add f of y to both sides, that gives you that f of x has to be greater than f of y. All right. Part E, I told you some of these had a bunch of parts. So part E, prove that f of x equals x for all x. And he has a hint here. Use the fact that between any two numbers, there's a rational number. Right, so here, assume that f of x is not x. Then that means that x is not rational because we already showed that it is for all rational values of x. Okay, and there exists a rational number in the rationals such that r is between x and f of x. That's by density of the rationals in the real numbers, meaning between any two real numbers you have a rational number. Right, so break this up into cases. If x is less than f of x, then there's a rational between x and f of x. But if you take f of all three sides of this inequality, that means that f of x is less than f of r. But since r is rational, that's the same thing as r. So that shows that f of x is less than r. Remember, the inequalities are preserved by this function because of one of the previous steps. All right, so f of x is less than r, but that contradicts the fact that r is between x and f of x. Okay, and same thing happens for case 2. Here we assume that f of x is less than x. Then again, there's a rational between f of x and x. Right, so if this inequality is true over here, that implies that r, which is f of r, right, because it's rational, r is rational, is less than f of x. So in other words, if you take the whoops, over here, if you take f of both sides here, you get that r is less than f of x. And again, that contradicts that r is between x and f of x. All right, so that exhausts all the cases. So that means that f of x has to be equal to x for all x. All right, and I think that was 317. What number was that? over here, 317. Okay. Next one. I think this is the last one for this video. Yeah, 320. There's two parts to this one. Part A says find a function f other than a constant function such that absolute value f of y minus f of x is less than or equal to the absolute value of y minus x. Right, so actually you can choose any linear function that has a slope that is less than or equal to 1 in magnitude. Right, so if you do that and you take the difference of f of y and f of x and the absolute value, you can simplify that to this, and because the absolute value of m is less than 1, that's less than the absolute value of y minus x, and you're done. And so any linear function that has a slope of magnitude less than or equal to 1 works. Okay, suppose that f of y minus, this is part B, suppose that f of y minus f of x is less than or equal to the square of y minus x for all x and y. Let me say, why does this imply that absolute value f of y minus f of x is less than or equal to y minus x squared? It works that way just by the properties of absolute values. I'll let you guys work that out. It's if you take this to be true and then multiply through by a -1, then you'll see that you get what you want. You get the triple inequality here. So I won't write that out, but prove that f is a constant function. All right, he gives a hint here: divide the interval from x to y into n equal pieces. So that's what I did. Here's the proof: let x, y be real numbers, and I'm assuming that without loss of generality that x is less than or equal to y. Right. Then the absolute value of y minus x is equal to the sum. This should be a j here. J going from 1 to n of j over n times the absolute value of y minus x. In other words, I'm breaking the number line. Let's see, can I write that out? So draw this somewhere. It's easy to see. So what I'm doing is, let's say this is x and this is y. I'm breaking it up into equal, pieces of equal length. So each of these will be like absolute value y minus x over n. If let's say that there's n pieces of endpoints in the partition here. So this one would be y minus x, an absolute value over n. This one would be 2 y minus x over n. Whoops, over n. This one would be 3 times y minus x over n, and so on like that. So that's all I'm saying there. All right, and so if we break up the interval y minus x into those subintervals, and I just made this definition here just so I don't have to keep writing this long expression out here. So let epsilon sub n equal this quantity here, just because it's easier to write. Okay, choose a partition of the interval from x to y, assuming without loss of generality, like I said, that x is less than or equal to y. Then, so this is our partition. This is what the partition looks like, right? You have x, then you have x plus epsilon sub n, x plus 2 epsilon n, and so on, down to x plus n minus 1 epsilon n, and all the way up to y. So like I said, just in the picture, I'm just breaking it up into those pieces. All right, for each of those subintervals, if you take the length of the consecutive points in the partition, for example, f of x plus j plus 1 epsilon n minus f of x plus j epsilon n in absolute value, that'll always be less than or equal to epsilon n squared. That follows from our assumption here that this is true. All right, so that means that the absolute value of f of y minus f of x is less than or equal to the sum from 1 to n of the epsilon n squareds. And if you sum these up, you get, that'll be n times epsilon n squared. So here, one of the n's cancels. And you end up with this expression here. So that means that f of y, the length of f of y minus f of x is always less than or equal to this positive number divided by n, right? And n, whoops, and n can be anything, right? So therefore, that quantity, the absolute value f of y minus f of x, can be made as small as possible, as small as we like, by taking finer and finer partitions, meaning, take more points in the partition. And that implies that f of y minus f of x is equal to 0, which implies that f of y is equal to f of x. Therefore, f is constant, right? And that's the last bit of problems that I did in chapter 3. So the next video, actually, let me just stop the screen share for a second. The next video I'm going to do is, which I already have the notes and everything written up for the next 2 videos. I'm going to do the next section in Schifrin. I'll do the notes first, then I'll do the exercises. I have all that worked out already. I just have to make the videos for them. And then we'll continue, with differential equations, then classical mechanics, then linear, and then we'll come back around to chapter 4 in Spivak after those are done. All right, guys, thanks for watching. Again, I hate to be annoying. Please like and subscribe if you like seeing content like this. Feel free to comment in the comment section if you like, and I'll see you guys in the next video. Thanks for watching.